In today's video, we are going to be looking at the solutions to second order homogeneous differential equations which have repeated roots. So to exemplify with this problem, we are looking at y prime prime plus 4y prime. Okay, the question has a problem over here. So this is a 4y prime and plus 4y equal to 0, and we want to obtain the solution assuming that y is a function of time, f of t. So auxiliary equation is, we have s squared plus 4s plus 4 equal to 0. Now, how did I get the auxiliary equation? I'll still repeat myself. There's a trick I normally use. Just replace any y prime prime with s squared, replace any y prime with s, and replace any y with 1. Okay, so this is the trick to get your auxiliary equation. And like I normally say, you don't have to use s as the variable for your auxiliary equation. Some people can use m, some people can use lambda, some people can use r, some people can use anything they want to use. There are a whole bunch of variables out there, but I love using s because it has a lot of insight to the nature of second order differential equations in general. Now, this trick actually is extensible in the sense that if you have a y prime prime prime, for instance, you can replace it with s cube, and a y to the nth derivative, you can replace it with sn, and so on. Now, why do we normally replace y with 1? Because y is like on its own, it's not differentiated, so the order of differentiation or the depth of differentiation is 0. So when you do s raised to the power of 0, just like we have been saying here, you're going to get 1. So anytime you see y, we replace it with 1. Is that okay? Now, this is our auxiliary equation gotten by replacing the corresponding derivatives with the variables and the exact powers, okay, or the orders of the terms that you're seeing. Here is 2 order, here is 1 order, and here is 0th order, meaning that there is no differentiation. So this is s raised to the power of 0. And when you want to solve this differential equation or using the auxiliary equation, you can just use what we know from factorization. Okay, so if you factorize this, you are going to get an s plus 2 and an s plus 2 equal to 0. This will give me s is equal to minus 2 twice. Another way of factorizing is to use the quadratic formula. S is equal to minus b, which in this case is minus 4, and plus or minus the square root of b squared, which is 4 squared, and minus 4ac, 4 times 1 times 4, then over 2a, which is 2 times 1. Okay, because a is 1. So when you solve, you have minus 4 plus or minus square root of 16 minus 16 over 2, and this is going to give me minus 4 plus or minus 0 over 2, and this is going to give me minus 2, okay, plus or minus 0. Okay, so this is minus 2 plus or minus 0. So s is equal to minus 2, or s is equal to minus 2, because minus 2 plus 0 is minus 2, and minus 2 minus 0 is minus 2. So s is equal to minus 2 twice. Is that okay? S is equal to minus 2 twice. So when we have repeated roots, how will it affect the nature of our solution? So you have to recall that for repeated roots where s1 is equal to s2, so we'll have that y will be equal to our arbitrary constant exponential minus exponential s1 t, then plus t, or like this, plus c2, then t exponential s2 t. Is that okay? So the essence of putting this t is because s2 is equal to s1. Is that okay? So if we solve this particular case where we got minus 2 twice, we are going to get our function y of t is c1 exponential minus 2t, then plus c2, then t exponential minus 2t. Is that okay? So this particular this particular polynomial helps us to address the fact that we're having a repeated root. Okay, now you are going to see of the uniqueness and existence of this particular solution much later in the depth of this course, but for now just take it like this. You can actually go ahead to factorize. Y of t will now be c1 plus c2t all into exponential negative 2t. So you can actually leave your solution in this form. Okay, so this is the solution for repeated roots. So we're going to take one more problem on repeated roots with the speed of light. So in problem 2, we want to solve y prime prime minus 6y prime plus 9y equal to 0, where y is a function of x. Okay, so the auxiliary or characteristic equation is, okay, I'm sure you've gotten it already. So let me use another variable just for flexibility. I want to use lambda, so I have lambda square minus 6 lambda then plus 9 equal to 0. So the trick is replace every y prime prime with lambda square, replace y prime with lambda, and replace y, since it has a 0 derivative, with 1. So this is the trick for getting the auxiliary equation very quickly. So after getting the auxiliary equation, so I can now solve using what method of quadratic formula. Lambda is equal to minus b minus 6 plus or minus the square root of b squared minus 6 squared and minus 4 ac1 then 9 all over what 2a, 2 times 1. So you have lambda is equal to 6 plus or minus, what do you have, square root of, we have 36 minus 36 over 2. So when you solve, you get 6 plus or minus 0 over 2, which is actually 3 plus or minus 0. So lambda is equal to 3, or lambda is equal to 3. So this implies that lambda is equal to 3 twice. Okay, so for lambda equal to 3 twice, our solution y is equal to c1 plus x. Sorry, I should put the c2 first, c2x, and we now have exponential 3x. So this is your solution, just like we derived it in the first case. So whenever you have like repeated roots, okay, this particular independent variable here, this particular term usually multiplies one of the arbitrary constants, and an increasing factor of this or an increasing polynomial of this particular independent variable will continue being the case when you have like higher order derivatives. So we'll see that in a future example, but I hope you've understood how to deal with repeated roots now. Thank you very much for watching this video. Please like, share, subscribe, and hit the notifications to stay updated, and I'll see you in the next video. Stay safe. All right.